Welcome back, everyone. It is week 5, lecture 2. We're going to continue our series on research validity and talk about internal validity. So remember that we're in a series talking about research validity, and the whole point of research validity is to reach accurate conclusions with your research. And there was 4 pieces of this. So the first one was statistical validity. We talked about that last week. This week, we're going to talk about internal validity, and that is when dB differences are primarily attributable to the IB that you're studying, not other factors. So when you're confident in that, you've got internal validity. So how do you do that? You control sources of confounding. And so really today's lecture is mostly about sources of confounding. Next week, we'll talk about construct validity for causal conclusions, and then finally, external validity. So let's get going. So internal validity, again, is when dB differences are primarily attributable to the IB that you're studying, not other factors. The goal of your study, so like your dissertation, is to determine the effect of some independent variable on some dependent variable. So what you got to be thinking about is what else could be causing the change, if you see a change, in your dependent variable besides your independent variable. Those are the things you need to control for or adjust for in order to ensure that you have good internal validity. So if there are other factors, and we call those potential confounders, then there are plausible rival hypotheses besides your independent variable that can explain any changes that you see in your dependent variable. So for example, and this is a study I did, let's say you're looking at the effect of making new motorcyclists first go through a motorcycle training course, and what you want to see is whether this reduces their numbers of fatal motorcycle crashes in California in the years after the course is required in our state. However, let's say that during the time that they implement that law requiring new motorcyclists who are involved in a disproportionate number of crashes in our state, the legislature passes another law that requires all motorcyclists to wear helmets. Well, what do you have? You've got 2 plausible hypotheses that could explain any reduction or change that you see in fatal motorcyclist crashes. That is what we call a potential history confounder, another thing that occurred during the point of your study that can also explain differences that you see. So if fatal motorcycle crashes decrease, was it the course that they were required to take, or was it the helmet law? You can see the confusion that occurs because you've got competing potential explanations, and that's what we mean when a study has poor internal validity. So the threats to internal validity fall in 4 broad categories. So there are 4 broad categories of rival hypotheses for results that you find. First, there's causal ambiguity, and causal ambiguity is when you're unable to determine the exact cause of changes in the DV. And there's 8 different ones of those we'll talk about. Then there's subject reactivity. So subject reactivity specifically is when participants respond differently in your study because they know they're being observed or studied, and there's 14 of those. Then there's extraneous variables. So these are all the other outside factors that are somehow confounded with the independent variable, and therefore whose effects can't be removed from the independent variable when you see changes in the dependent variable, and there's 5 of those. And finally, we're going to talk about experimenter bias. So these are ways that sort of knowingly or not, the researcher or experimenter can alter the findings of their study, and there's 9 different ways that that occurs. So let's hit this. So overall, all these things cause problems with inferring that changes that you see in your dependent variable are due to your independent variable and only your independent variable. So the goal, again, of internal validity is to ensure that if you get to the end of your study and you see differences between your groups or some sort of effect, you are confident in concluding that those differences or that relationship is due to your independent variable, not other factors. So let's start with causal ambiguity. These are just 8 different ways that you just can't determine what caused the changes in your dependent variable. So the first one, and probably the most important, is self-selection bias. So self-selection bias is when either participants are allowed to choose the experimental condition that they're in, or they're assigned in some other fashion that's non-random. So it could be people who are referred, could be in that study we talked about with the court, where the judge sort of overrides the random assignment and assigns the worst offenders to a particular condition. Maybe it's just what people can afford. These are all different reasons where self-selection bias can become a causal explanation for your study. So the problem is that their choice, or the person who assigned theirs choice of which study condition a person gets into, may reflect some sort of underlying difference that could explain your findings. So for example, in a study of differences in the effectiveness of two types of therapy on obsessive compulsive disorder, people with different severity may be referred to rational emotive therapy, which is known to be particularly effective for them, whereas those that are less serious cases of OCD may be referred to client-centered therapy. So if you compare those two conditions, well, you've got a pre-existing difference between the folks who were assigned to the two types of therapy in the first place. So if you get a difference, was it due to how they were assigned, or was it due to the type of therapy? So you don't know. That's the problem, and that's what we're talking about with internal validity. So then there's extraneous variables. So these are all the other variables other than your independent variable that are related to the dependent variable, and they might have affected the outcome and hence could explain the differences that you see. And when you have such variables in a study, we call it a confounded study. That is, when the effects of extraneous variables are mixed with effects of the independent variable and cannot be separated, that's what we call confounded or confounded study. So, for example, let's say you're studying the effectiveness of two different fifth grade reading programs using two different classrooms at a school, two different sets of students, and two different teachers. And let's say you didn't randomly assign the students within each class to the type of reading program. Well, the teachers probably differ in their teaching style, why they chose each program that they decided to use, and so forth. So if you get differences between the classrooms, was it the reading program, or was it differences between the teachers, the students, the classrooms, etc.? The point again, you don't know. You have extraneous factors that could explain differences that you see. Then there's demographic variables. So the idea of demographic variables as a cause of causal ambiguity is that just because in a study you find that something differs as a function of a demographic variable, say sex for example, it doesn't mean that the demographic variable caused the differences in the dependent variable. Yes, they differ, but was it really, literally the underlying demographic that caused that, or was it other factors associated with it, for example, socialization? So let's say, for example, that just because men and women may differ on some variable, it doesn't mean that literally biological sex causes those differences. It could be biology, but it could also be, as we talked about, social differences in rearing, could be differences in modeling, opportunities, and so forth. So the argument here is that when you see differences as a function of a demographic variable, it's not necessarily a causal relationship. It could be associated with third variables that are associated with those demographic variables. So it's like a third variable confounding problem. So then there's history effects, and this is the one we were talking about when I brought up the example of a motorcycle safety program. So a history effect is any event that occurs between measurements of the dependent variable, and it's not part of the experiment, so you didn't do this on purpose. But these things that occur could also explain the findings that you get, because you can't separate them from the effects of the independent variable. So the real world changes that occurred during the period of the study, so they're particularly a problem in repeated measures designs or longitudinal designs. So plane crashes, wars, rioting, newspaper articles, law changes, etc. Law changes like the one where the helmet law went into effect in that example earlier. Now, history effects can also be a continuation of some already occurring patterns. So, for example, if things are going down over time, like a trend. So, for example, young drivers in California have been getting licensed at a lower rate ever since the 70s. It's been going down. Well, because fewer are getting licensed, fewer are getting in crashes. So any study that evaluates pre-post designs over a long enough period is going to show lower crash rates subsequent just because there's fewer 16 and 17-year-old drivers on the road. That's a continuation of an existing trend. It's a history effect that, you cannot differentiate the effects of that from the effects of the independent variable. And this is why we need control groups or comparison groups. They help us control for history effects. So another group that's in your study that doesn't get the treatment of interest, that you can say, all right, look, they changed maybe a little, but in my experimental group they changed a lot, so therefore this isn't all just history effect. It's got to be some actual effect of my independent variable. So for example, let's say you're looking at the effects of a quit smoking program on smoking, and it's a pre-post design, so you measure them before and after the smoking program. But what if someone famous dies of lung cancer during the experimental period, or a new drug's introduced that's over the counter that helps people quit smoking, or some big study comes out about some new cancer that's caused by smoking? If you get differences, are they the result of your quit smoking program, or are they the result possibly of these history effects? They could have influenced their smoking behavior rather than your quit smoking program, and so therefore they are a potential explanation for any differences you see pre to post. Then there are maturation effects. So maturation effects are just all the different things that occur because people change over time. So when participants change during the research in ways that can affect your dependent variable, you've got a problem with maturation effects because they're systematic changes of the participants over time. And so you can mistakenly attribute DV differences that you observe to your independent variable when really it's just a maturation effect. So this is the usual stuff. So people get tired, fatigued, they grow up, they get more mature, they get hungry, children become more analytical, people get bored, you're tired, etc., and so forth. So later performance in a longitudinal study in particular is going to reflect those effects of those changes in addition to any effects of your independent variable. So let's say one of the things we know from traffic safety research is that drivers become safer at 25 years old. But you know what? It's not necessarily because magically at age 25 you have enough experience that you're a safe driver. Other things occur by the time, sort of on average, by the time you're 25 years old. People are getting married, they're having kids, they've got careers, and so maybe they tend to be safer drivers at age 25, not because they're magically more mature or their brain is myelinated or whatever it is, but it's just they've got more to lose. They've got things they care about, and so it has to do with all these external factors, not, again, literally just the process of maturing or age. So randomizing people to groups in your experimental study is one of the ways that we fight these sorts of maturation effects, because they're still going to occur, but at least they occur equally between the two groups, and you expect a bigger effect in your experimental group. And again, using between subjects designs also helps with this, instead of using repeated longitudinal designs. So then there's something called pretest sensitization, and these are also sometimes called testing effects. So pretest sensitization is when participants react differently later in your study because they take pretests or otherwise repeatedly sensitized to the dependent variable. So, for example, let's say you have folks take a pretest on their attitudes towards the homeless before watching a video. Well, just taking the pretest itself may sort of make them introspective about their thoughts about homeless people rather than any effects of your video, which is supposed to influence their opinions on homeless folks. So it's actually the act of having to take a questionnaire about attitudes toward the homeless that changes their behavior, not your video that's supposed to elicit a response. So this is when your pretest sensitizes subjects for example, to the purpose of your experiment. So let's say in your quit smoking program, for example, you have folks keep a diary of how many cigarettes they're smoking on a daily basis. That by itself, regardless of any other components of your program, may sensitize them to the fact, wow, I'm really smoking a lot. So having participants keep a diary as part of a treatment condition may be enough to actually change their behavior regardless of any effects of a treatment that you implement. So how do we deal with this? Well, we include control or comparison groups. That is, another group who, in this example, would keep a diary but doesn't get the additional treatment. So if the treatment's effective, both groups could have effects of pretest sensitization, but you'd still, again, expect a bigger reduction in smoking in those who get your treatment that's special. So another way to fight it is don't do pretests. So just do what we call a post-only design or a post-only intervention. So you randomly assign two groups. One gets the treatment, one ends up in the comparison group, and you just measure them one time afterwards. There is no pretest to sensitize them. So the downside, so the good part of this is you don't have pretest sensitization. The downside is you have less statistical power. So remember that within groups designs tend to be more powerful. Then there's instrument decay. So instrument decay is when characteristics of your measurement instrument change systematically over time. So this is particularly true when human observers are used to measure behavior. They, for example, get better at measuring things. They get bored at measuring things. So if you've ever been driving and gotten off at an exit and seen folks with clipboards and orange vests at the top of the off-ramp or bottom of the off-ramp, depending on where you're at, sort of watching cars get off the freeway and they're recording things, what they're doing is the annual NHTSA seatbelt survey in California. And when these folks first start doing the data, it could be the case, or collecting data on seatbelt use, it could be the case that they're super vigilant, right? They're brand new at the task. They just got trained. They're doing a really good job. And so they might be better at collecting that information near the start of the story and less so near the end of the study. So that could make a treatment effect. For example, some sort of advertising campaign that's supposed to get you to like click it or ticket, those signs that they use for the Megan's Law thing. They put those signs out, but if they're collecting seatbelt use better or more effectively at the start and poorer at the end because they're getting kind of bored of doing this or it's hot, it could show that effects are actually less over time. So that is an example of instrument decay. So alternatively, the opposite could happen, right? So they could get more experienced or better over time at recording behaviors. So seatbelt use, later on, they're really good at catching folks who it's the vehicle's tall or whatever, and they're better at capturing whether the person was actually wearing their seatbelt. And so seatbelt use appears to go up over time when really it hasn't changed at all. It's just they're better at doing it. That again, it's not decay, it's just instrument change, I guess, technically. So literally what instrument decay usually refers to is changes in electronic or mechanical measurements. So, batteries going slowly dying on a weight scale used to measure participants, that sort of thing. Cameras getting dirty, that sort of thing. So one of the most famous ones is regression effects or statistical regression. And this is sort of the tendency for extreme things to be less extreme when they're remeasured over time, regardless of an intervention. So this is that effect you see when two really attractive people, for example, all things being equal, are more likely to have a less attractive kid than either of them. And the opposite happens as well, right? You're like, two very unattractive people have a very attractive kid. And that's because they're very extreme on something. So when things are remeasured, they have a kid, things tend to move towards the average attractiveness in this example. So the idea is that extreme groups will move towards average even without your intervention effects of your independent variable. So this happens when you choose your groups specifically based on the fact that they're high, super high, or super low on something. So for example, heavy smokers are going to tend to move down towards the average smoking level and make a treatment look effective over a long period of time, even if the treatment is not effective. They just tend to move towards the average of smokers in this case over time, period. So Elkhorn Boulevard in Sacramento, for example, had extremely high fatal crash rates a couple years ago. So the city took it upon themselves to do all sorts of interventions and have lots of police patrols out there and Caltrans interventions to try to reduce crashes on that roadway. But to be honest, all things being equal, after an extremely odd year, like an outlying year where they had so many crashes, even if the city did nothing, it was likely that the next year the crash rate was going to be lower on Elkhorn Boulevard. Why? Because things tend to move again back towards the average over time. So this also occurs when unreliable tests are used to measure things, and so you get extreme scores for people. So when you measure them a subsequent time, their second score again tends to move towards the average. So the next major topic is subject reactivity. And there's 14 of these, and there are ways that participants respond differently in a study because they're being observed or studied, usually because they know it. So sometimes what happens is they try harder or they react differently because they know they're being watched and that their behaviors are being recorded. So for example, the first one is what we call demand characteristics. And this is when the data collector or the experimenter gives, it could be overt, but typically it's subtle cues about how they expect participants to react, and the participants react accordingly. So for example, if you give people a drug and you tell them, hey, this drug's going to enhance your sex lives, you're going to find that magically, even if it's literally a sugar pill, for some portion of subjects, they're going to report that they have enhanced sex lives. This is like the way that late night infomercials work, right? And so if the placebo effect is real, I guess is the way to say this, people will respond in the way that they think the researcher or they're told they should respond. So how do you control for this sort of thing? Well, you do blind research. So blind research, first of all, is where participants don't know what condition they're in. You've probably never heard of that. What you've probably heard of is double-blind research. So double-blind research is even better. This is when not only does the participant not know what group they're in, but neither does the person who's collecting the data or administering the treatments. That's what double-blind research means. Like all the pills look the same, no one knows who's getting what, who's actually involved in the data collection or treating. So those inert pills that we give to folks that, or pill, or it could also be just an intervention in general. We talked about at one point how you can use decaf coffee versus coffee, and a study of the effects of caffeine on memory. Placebos are these inert substances or interventions that we will give to control groups sometimes that otherwise look like the treatment but have no actual intervention effect on folks. So obtrusive observation is another problem that results in subject reactivity. And this is just what it sounds like. You're observing them and you're intrusive about it. So participants react differently because of the literal presence of the researcher recording their behaviors. So I've had some experience with this in my world. They can also react differently just because the measurement instrument is intrusive, even if there isn't literally a person there. So, for example, I had to do a thing when I worked at the state where an IO psychologist was doing a study of what a research analyst did during the day. And so they followed me around and sat in my little cube and all day long recorded what I did, like every minute of the day. And it was honestly the most, I got the most work done that day at the state than any other day I ever worked there because I changed my behavior because I knew I was being watched, right? So it was truly my most productive day. So how do you avoid obtrusive observation? This is going to shock you. You can do unobtrusive observation, and that's where participants are not aware that they're being observed. So the problem with that is it's hard to get informed consent, and there's problems with privacy. And you can also use unobtrusive measurement tools. So use things that don't sort of make it obvious what it is you're measuring. So if you ever take questionnaires, or some people do this with questionnaires where they're really only interested in one or two things, but there's 15 questions on the questionnaire. And it's because what they're trying to do is bury deep down in there the three questions that they're actually interested in, so it's not so obvious. And that would be an unobtrusive measurement tool. So resentful demoralization is just the bane of existence for education researchers. And this is what happens when control groups are given boring experiences. And so there's a treatment group and then the control group, and the control group gets something that's just really boring and mundane and not exciting at all. And so as a result, they perform poorer than they would have if they had just been in a normal sort of everyday experience. So this particularly is likely to happen if they know the other group, the treatment group, is getting something that's cool or fun. So let's say at a 5th grade classroom, the classroom next door, they can hear it. They're getting cartoon math. And so they're learning math by watching cartoons. And your classroom just gets boring repetition of doing, math problems ad nauseum. So what could happen is those who are getting the boring problems, they perform even worse than they normally would have because they know they kind of got the short end of the stick. We call that resentful demoralization. So they can hear the fun videos, and so they just get mad and perform worse. So the flip side of that is compensatory rivalry. So sometimes control groups know they got the short end of the stick or the boring intervention, and so they work extra hard to compensate for the fact that they got this lamer treatment. So they know that they didn't get the fun math program, so they work extra hard to perform, to show that they can still perform well. And so again, this is the flip side of resentful demoralization. Then there's treatment contamination. So this is, again, exactly what it sounds like. The treatment gets contaminated. And this occurs when participants who are in different groups or different levels of the independent variable talk to each other and ends up messing up your attempted manipulation of the independent variable. So let's say the treatment group watches funny videos while the control group watches boring commercials. But if at some point the two groups talk to each other, it could affect the measurements that you get for the dependent variable in ways that you didn't predict. So it can, for example, result in resentful demoralization, or just your whole attempt to manipulate the independent variable failing entirely. So then there is characteristics of the experimenter, which is often called the biosocial effect. And this is just simply, participants react differently sometimes due to how data collectors look or act. So participants may be more or less honest with a data collector who is more similar to them in terms of age or sex or whatever. So we would call those biosocial effects. So one way to fight this is depersonalization. So you minimize the interaction between the experimenters and the participants, for example, by using paper questionnaires or online questionnaires to depersonalize that interaction and therefore minimize biosocial effects. So one of the most famous ones is what we call the Hawthorne effect or the placebo effect or the novelty effect. Any of these things, it's the same effect. And this is when participants react differently because they know they're being studied and you change something. So it's kind of like a sub level of expectancy effects. So it's named after an industrial organizational psychologist in a study back in, I think it was the 30s or 40s in upstate New York, in a light bulb factory where the goal of the industrial organizational psychologist, Hawthorne, was to improve the performance, get more light bulbs made, basically. And so what happened during the study is everything they did resulted in increased productivity for a short time. They turned the lights up. You know what? They made more light bulbs for a couple days, and then it kind of went back down, regression, the mean average. They added a 15-minute break every couple hours, and performance went up, and then it went back down again. Every novel thing they introduced resulted in some increase in performance for a short amount of time. And that's why it's called the novelty effect as well. So those signs, for example, on the side of the roads that report your speed back to you have what we call a placebo, Hawthorne, or novelty effect. And that initially when you see it sort of giving you feedback about how fast you're driving, people slow down. But then they realize after a while, hey, I didn't get a ticket in the mail And so they start to lose their effectiveness after a while. It truly is a novelty effect, not a long-term effect. So the placebo effect, folks, is real. People do actually get better just by thinking that they're going to get a treatment or they're in a study, that sort of thing. I'm going to get help. They will get better. Some portion will. And this is, again, why some doctors still to this day prescribe sugar pills. A fair portion of prescriptions, there's actually a lot of stories here, are inert substances that they tell people will work, and the effect is that they actually do work for some portion of people. So then we have order effects, and order effects are a problem in studies where you have multiple independent measures or multiple dependent measures. And so in particular, in repeated measures designs, they can affect responses to the dependent variable. Repeated measures designs, again, are where you have the same people in the different levels of your independent variable. And what happens is because if you always present your independent variables in the same way, say there's 3 different types of cookies they eat, peanut butter, oatmeal, and chocolate chip, it could be the fact that because they're always eating the peanut butter first, it affects how they experience the taste of the subsequent flavors. And so, and it happens with questionnaires too. You can pretest sensitize them if you're looking at, say, religiosity and abortion, and you always have them first do a religiosity questionnaire, then the abortion questionnaire. You can get different effects than if you flipped it around, right? And so you can either randomize the order that the independent variables or the dependent measures are presented to participants, or you can do what's called counterbalancing. And counterbalancing is randomly assigning them to a different order. So if you got A, B, and C, you come up with all possible orders. There's A, B, C, there's A, C, B, there's B, A, C, B, C, A, etc. And you randomly assign participants across those different orderings of things. Then there's the Orne, or the good subject effect, again named after someone. And this is sort of like that response set we talked about where people try to respond in positive or feel-good ways. So this is when participants try to figure out what it is you want them to do. So they're trying to be good subjects, and they figure out your hypothesis or what they think your hypothesis is, and they respond in ways that are consistent with what they think you want them to say or do. So, for example, if you present material to them and you call it arousing, not so shockingly, you'll get some portion of people who will report more arousal regardless of whether the material actually is or not. They're trying to be good subjects and trying to help you with your research. If a lawyer, so this is sort of the classic example of this is the work in eyewitness research. If lawyers describe a car crash as 2 cars smashing together instead of colliding or something that's less sort of dramatic, they tend to get more feedback that yes, it was a severe crash if they say smashing rather than colliding or hitting, that sort of thing. And that's classic research in social psychology. So the opposite of the good subject effect is the bad subject / screw you effect. So that is literally what it's called in the textbooks. And this is when you've got participants who are deliberately just trying to undermine your study. So for example, the classic, 8th grader who writes lots when you ask them for their sex on a survey. So this happens when people think the research that they're forced to do it, or they think it's meaningless or stupid or boring, or you coerce them into doing it. Like intro to psych students, this is one of the big problems with using intro to psych students as your research pool, is that they're not particularly motivated and they may just take it out on you. So then, continuing with subject reactivity, evaluation apprehension is when participants are uncomfortable answering certain questions, so they use a response set, such as the social desirability response set, or they just give you evasive answers. The result is bad data, of course, and this is why, or to reduce this anyway, you want to ensure confidentiality, make people, if you can, make data anonymous when you're collecting things, particularly when you're studying subjects that are sensitive. So test sophistication is what occurs when people learn to become good test takers or better at completing DV measures, and then they can more easily do good subject or bad subject effects, lie about things, etc. over time. So this is particularly apt to occur when you have repeated measurements in a study. They can fake higher or lower ability on a test or a psychological measure just because they got sophisticated at taking it. They can learn to finish faster by answering a particular way. So for example, each year I have to take a survey for my work about whether I exercise and whether I eat right and that sort of thing. And I realized early on, and it's again supposed to be anonymous, but it's never anonymous, that if I answered in a particular way, I could finish it and get back to what I really want to do in my work. If I told them, no, I don't exercise, they don't ask more exercise questions, you're just done. So I got test sophisticated and I'm giving them garbage data. So, and that's the example here. I don't have to do the exercise section if I just tell them, no, I'm not. or sorry, I do exercise 3+ days a week. So research sophistication occurs when participants, they try to guess the nature of any sort of deception, or they guess that deception is being used in a study, or they guess at what the hypotheses are. But the problem is they may change their responses as a result of that. So now that you have taken this course, for example, you may react differently when you're taking surveys out there in the real world. So the way you deal with this is through random assignment to treatment and control groups. And then importantly, you want to use credible activities for control groups, because then folks are less likely to guess that there's deception or there's some real treatment going on, and it helps you avoid this problem. Memory or practice effects are effects that occur because participants perform better or they get more similar because they've already completed some sort of task. So for example, if I ask you to take a test twice, you're likely to perform better the second time, not because you actually learned anything per se, but just because you're getting better at taking the test or you memorize some of the questions, etc. So one of the reasons that GRE prep courses seem to magically work, for example, is that especially for folks who are taking a second-time test, they tend to get better at test taking, period. They get practice effects. Just taking tests or performing a task, you get better at that task, and they tend to do better. Even if they didn't really learn anything, they learn to be better at taking the GRE. And that has, a meaningful effect. So finally, we're going to talk about extraneous variables. So these are just 5 other ways that variables are confounded with the independent variable, and so their effects on the dependent variable can't be separated out from those of the independent variable. So subject characteristics is one of these, and these are just all the sort of various things about participants that are related to the DV, besides the independent variable, that could vary systematically between your groups. So we know, for example, that age is strongly associated with health, especially in the work that I do in epidemiology. So if, for example, even though I randomly assign participants to different drug treatment levels, I get an average difference in age that is a subject characteristic, I could have age confounding effects on my dependent variable, even if I randomly assigned and did a good experimental design, because I have differences in subject characteristics. So again, the goal is to use random assignment to try to equalize this, but it doesn't always work. So you can do a pre-post test design so you can actually evaluate whether there's differences in subject characteristics. Another method is to use that stratified random sampling method that we talked about, where you ensure you have equal numbers of some important subject characteristics. So for example, I would equalize the number of men and women in treatment conditions to ensure that sex wasn't a confounder, a subject characteristic confounder for my study. Or alternatively, what folks do, if you can't randomly assign, you can always measure those things that are potential confounders that are subject characteristics, and you can adjust them using something called covariate analysis. So mortality is one of the classics of internal validity issues. And mortality, I mean, it means death, but it also means just loss of folks. They drop out of your study, so they're dead to you, I guess. This is when you lose participants because they don't want to continue. They relocate. They literally die. They just become bored. And this is a problem, for example, in most dissertations that are online surveys using SurveyMonkey, because folks will complete a couple questions and then sort of leave. And like you don't actually get to use their data, but your committee is going to ask you about folks who dropped out, and it becomes sort of your problem. So yeah, Fight Club reference, which I can't remember. Oh yeah, okay. Over a long enough timeline, the survival rate for everyone drops to 0. So let's say that persons who really want to quit smoking stayed in your smoking cessation program, while those who are not so serious dropped out. That could, for example, make your program look more effective than it really is, because the people who really wanted to quit stayed in your program, even though maybe it wasn't all that great, or it's kind of boring, or it cost too much money, but they were really motivated. So you're getting an effect for those who stay, those who don't experience mortality, where they differ in motivation from those who drop out. And it can invalidate your research conclusions due to the fact that the folks who drop out oftentimes differ from those who stay in ways that are important for explaining differences in your dependent variable. So teens, for example, who need to work to help their family may drop out of a drug treatment program, and those teens may differ from those who stay in the program, and so effects you get could be confounded by motivational differences again. So this is a big problem in long studies or longitudinal studies, so I don't recommend doing either of those for your dissertation because you need to get out of school. So even worse than normal mortality is differential mortality. And this is when you've got a study and it's got 2 or more groups, and people are dropping out, but they drop out of one group more than they drop out of another group. It's differential. The mortality is differential, hence the name. So what this means in nerd language is that mortality is confounded with the independent variable. It's confounded with treatment type. So let's say, for example, you're looking at the effect of shock therapy versus, counseling on depression. So one of these groups you think you're more likely to lose people out of than the other, you bet you're more likely to lose people out of shock therapy. And so then the question remains, if you get a difference in depression levels after treatment, that is shock therapy or counseling, was it due to the folks dropping out differing from those who remained, or was it due to the actual treatments themselves? So, for example, if 50% drop out of shock therapy, which, wouldn't shock me, haha, can you even conclude if shock therapy is effective at all? So it's a big problem in studies where one treatment is less desirable or clearly not effective or goofy versus the other. So this is why you got to make sure you use, good comparisons or good control treatments. So I had this occur in a study, for example, when I worked at DMV, and we were looking at online driver education versus classroom drivers education. And there's actually 2 more groups, but that's enough for didactic purposes. We got a way higher dropout rate of those who were randomly assigned to classroom driver education. They wanted to sit home and do the online course. And so when we had this differential dropout rate, and we show, for example, that those who went to online did better, was that an effect of differential dropout, that the folks who were on the online were particularly motivated, or was it due to the actual difference in the teaching methods themselves, which was what we were trying to actually determine. So then there are what we call generational or just age cohort effects. So this is when you have differences between generations of people, so growing up in different generations, that are confounded with your independent variable. So for example, you might find that there are differences between older and younger folks, but it may have nothing to do with age. It could have to do with having had different experiences in life that are associated with being one particular age cohort versus another. So this tends to be a problem in cross-sectional studies. Cross-sectional studies are where you go out at one point in time and you get different age groups and you compare them on something. So it was a problem in our driver research in that older drivers, not all of them grew up in cultures that had cars, or their families didn't have cars, or they weren't driving their whole lives. Whereas we have younger drivers who, for the most part, they've mostly all had cars in their lives their whole life. The car culture is sort of part of their experience. So if you get differences between older and younger drivers, is it age, or is it the fact that they grew up under different experiences? So it's also a problem in longitudinal studies where, again, when you see changes over time, so that's where you follow people over time, uh, it may not be age differences that are causing those differences, but experience differences. So it could be not literally, again, like subject characteristics, they're getting older, they're getting more experienced at things. So there's what we call compensatory equalization. And this is, again, sort of the bane of education researchers. And this is when other sort of, sound like Scooby-Doo, but meddlers outside of your study try to improve your control condition to make it more fair or more fun or more interesting to control subjects. Like they mess up your study and they water down your control treatment. So let's say you're looking at a study using Khan Academy videos versus textbooks to teach math to fifth graders. And the teacher in the control group, that is, it's just the textbook, they don't get the Khan Academy videos, they know that, or they hear that in the break room that the other class gets to watch these cool videos. They may try to compensate for the fact that their students in their group didn't get the fun thing. And so they bring math computer games to his or her class, right? Because they feel bad that the students aren't getting the fun instruction. They're compensating to try to, and it ends up in equalizing differences between the groups, hence compensatory equalization. So sometimes what happens is the controls perform even worse because they know they're not getting the cool treatment, right? They can hear the videos next door. And again, that's what we called resentful demoralization earlier. So the final topic for internal validity is experimenter bias. And this is 9 ways that you, the experimenter, can mess up your findings of your own study, again, intentionally or not. So one not so obvious one is observer differences effects. And this is just systematic differences in the errors made between observers. So this occurs when you've got different observers or different data collectors or different data collection instruments in your study, and they just differ from each other. So let's say, for example, in your study where a stopwatch is used, one of your 2 data collectors just tends to start the stopwatch a little bit earlier than the other data collector. You've got what we call an observer difference effect, and so you will find a difference in times anyway between your groups if you look at the folks who got that particular experimenter versus the others. So let's say in those seatbelt studies that we were talking about earlier, we're at the top or bottom of the off-ramps. One researcher kind of never bothers to try to count lap-only belts, which are sort of old school. They only count ones where there's a shoulder belt, and you're going to get differences in seatbelt counts or count rates between that experimenter and the others, just because you've got observer differences. So how do you fight this? Well, you pre-train your data collectors, or you ensure that your data collection instruments are equivalent, and you build what's called inter-rater reliability. That's how you avoid this problem. So one of the it just fits in somewhere is the intentional effect, and this is when there's just straight up deliberate dishonesty or sloppiness in data collection. People making up data, doubling your data, that sort of thing. This is, I mean, it's really fraud, but it has a name here. It's called the intentional effect, and it's another way that experimenters bias their studies. So faking data, or not coding data reliably, or coding things differently, the King's game is on TV, whatever it is an intentional effect. So continuing, there's the interpreter effect, and this is similar to differences in data recording because this is systematic interpretive errors between data collectors. So for example, in a master's thesis I helped a lady with, she had 2 people who were rating aggression in apes. And one of the person maybe they tended to rate certain behaviors, just sort of pushing or whatever, as aggressive, whereas the other said, that's not really aggressiveness. And so they would interpret that differently and not record them as aggressive acts. Again, how do you fight this sort of thing to avoid the interpreter effect? It's pre-training and building inter-rater reliability. So in studies I've been in, for example, they have two people, they'll record the apes, for example, and have two people independently rate how many events they got, and then they compare their ratings, and they would talk out differences until they built up where they were getting the same scores repeatedly over time to different videos. So the biosocial effect is when there are demographic or biological characteristics of the data collectors that affect the participants' responses, or vice versa. That is, demographic or biological characteristics of the participants that affect the data collectors, how they record things. So, for example, a male interviewer may get different results than a female in some survey of sexual habits and vice versa. And we call that biosocial effect. So the psychosocial effect is when there are differences in data collectors' interpersonal styles that affect the responses. So it differs from biosocial in that it's not, biological characteristics. It's sort of how they interact and communicate that affect participants' responses. So as you might guess, an anxious experimenter who's collecting data may get different results than a calm one, for example, right? Come on, give me an answer. You're going to get different results if someone's just patient, right? So we call that a psychosocial effect. There are also situational effects where the results are unique to the situation being studied. So you can't replicate them because they were just specific to that situation. So let's say that, for example, a researcher uses their friends in their dissertation or study. They may get different results than if they use total strangers. We call that a situational effect because it's specific to the situation of the data collection. Modeling effect is usually unintentional, but it's when researchers offer sample answers or they demonstrate a procedure and it introduces idiosyncrasies that are then modeled and repeated by the participants in the study. So if a data collector, for example, models that you can be goofy in your responses, you're more likely to get goofy responses to your study, right? That should make sense. Then another one of the most famous ones, you can tell these ones always have multiple names, is the experimenter expectancy effect, or the Rosenthal effect, or most famously, self-fulfilling prophecies. So research for these come from Rosenthal at Harvard University over several decades, where they found that data collectors' expectations about how things are going to turn out influence the participants to behave in ways that are consistent with those expectations. And it's, subtle things that can actually have effects. So for example, let's say the experimenter knows which person got a real drug versus those who get placebo. They could give subtle hints that their performance should change. So you're feeling better today, right? To those who got the real drug versus those who got placebo. They're not really intending to bias their study, but they end up doing so. So you end up with a self-fulfilling prophecy where they behave in ways that are consistent with how the experimenter communicates they should behave again. So another example, teachers who expect students to do well probably treat them differently than students they don't expect to do well. And that results in differences in performance regardless of what program they're in or what treatment they're in, etc. So experimenter drift is when there's just sort of gradual change in the way that subjects are treated over the course of the study. So it's kind of like an instrument decay or a researcher change. So data collectors may read things faster over the course of the study, or just differently, or more specifically because they learn they need to, or they don't record things as consistently. So you get changes over time that may look like effects of your independent variable, when in reality it's just drifting. It's like instrument drift, but for the experimenter. So how do you fight experimenter bias? What are the ways that you can actually reduce it? Number one is double-blind research. So this is why this is sort of the standard for clinical trials in epidemiology, for example. Again, neither the participant nor those persons who are collecting the data or administering the treatments know what condition any particular participant is in, so they can't therefore bias it with expectancy effects. Use blind raters to record events. So if they're like watching videos, for example, and like the monkeys again or the apes again and recording aggressive behaviors, you don't let them know what it is you expect them to find. That's a really bad idea. You have them be blind to what the purpose of the study is and just teach them how to rate things. Using standardized instructions, standardized procedures, training people beforehand is going to increase your consistency and reduce your experimenter bias. And, overall, just minimizing interaction between participants and researchers is a great way to reduce experimenter bias, but not perfect. And you have to remember that if you have multiple experimenters or data collectors, you have to do follow-up training. So just building initial inter-rater reliability is insufficient. You have to ensure that there isn't subsequent drift over time in how they're recording things or reading things or whatnot, so that you have consistency across the entire study. So finally, in terms of avoiding threats to internal validity, which study design, we've talked about a couple of them, which study design do you think is the best for ensuring that studies have good internal validity? Again, you get to the end of the study, if you see differences in the DV, you're confident in saying those differences are due to the independent variable assignment of folks, not to other factors. So which design? So descriptive studies, again, are studies where you're just describing things. It's like the most unsurprising name in this entire class, I think, for anything we talk about. You're not even trying to infer causality in descriptive studies. You're just describing groups or events or phenomena, right? So that one's not going to be the best for inferring causality. That is ensuring you have a good internal validity. Correlational studies we've talked about, and in correlational studies you're just looking at the relationship between naturally occurring variables, and it's sort of like a meme that your stats professor says you cannot infer causation from correlation, right? So again, correlational studies are not the best for ensuring internal validity. Now, quasi-experiments, that is where you do have a design with separate groups. You got an independent variable and a dependent variable, but the independent variable is quasi-experimental. That is, you take folks naturally in what group they're in, or you let them self-select, and you compare them on the dependent variable. There is no random assignment. You're looking at intact groups. And so there are many sources of rival hypotheses for quasi-experiments. Now, one thing you can do is something you'll learn about next semester, which is covariate analysis to try to equalize groups on known potential confounders. But what about all the other stuff you don't know about? How do you equalize on that if you don't even know about it? Bottom line is you don't. And so quasi-experiments are not that great for inferring causality. And given there's only one left, you're probably guessing true experiments. Yes, you're right. That's where the researcher randomly determines not only the levels of the IB, but they also determine what levels folks are assigned to, and they can use other controls to eliminate potential confounders. That is your number one way of being able to say this study has good internal validity and any differences I see are due to the independent variable. And so it is the most resistant study design regarding threats to internal validity. That's it.